In this video tutorial, we will introduce the concepts of salt hydrolysis and buffer solutions. Before we begin, let's do a warm-up question on pH calculations involving weak acids and strong acids. But if you want to skip straight to the lesson, by all means, the time indexes are written in the description below the video over here. Otherwise, press pause, and when you are finished solving the question, press play and we'll work on the solutions together. Alright, so the question asks 140 milliliters of 0.250 mole per liter HCl is added to 375 milliliters of 0.450 molar acetic acid. And then it goes on to ask what is the final pH of this mixture. Now a common mistake that students will make is they'll think that the hydrochloric acid reacts with the acetic acid, but that doesn't occur. Take a look at this. If you had a reaction over here, it resembles a double displacement reaction. But during a double displacement reaction, the cation will switch places, and in the end, you'll find that absolutely nothing has changed between the reactions to the products, and that's why there's no chemical reaction over here. So no reaction, that's not the proper way to solve this equation, or this question rather. Instead, we'll be using the equation pH is equal to negative logarithm of the H plus concentration. So remember, H plus really means hydronium, H3O plus. We're just using a short form for this. Now, because the hydrochloric acid and the acetic acid are both contributing H plus ions to the solution, really the equation is negative logarithm of whatever H plus is donated by the HCl and whatever H plus is donated by the acetic acid. So let's start off with how much HCl is donated by the hydrochloric acid over here. If you recall, HCl is a strong acid, so it's part of the list of the 6 strong acids you have to memorize. And because it's a strong acid, by definition, it completely dissociates 100%. So there will be no HCl molecules left behind. All of them will dissociate into H plus ions and Cl minus ions. Since it's a 1 to 1 to 1 ratio, we can use the amount of HCl to tell us how much H plus is contributed to the solution. So mole is equal to concentration times volume. We have the concentration of the HCl, 0.250 molar. We have the volume, which is 140 milliliters, but don't forget, you must convert it to liters in order to cancel out the units. So that's another common mistake students will make. Once you multiply these two numbers together, you get 0.0350 moles of H plus donated by the hydrochloric acid. Now, when we try to punch it into the pH calculations, don't forget that it has to be the molar concentration of H plus ions. Now, concentration is dependent not just on moles, but also volume. And to this, because we added 2 solutions to this beaker, we now have a new volume of 515 milliliters. 375 from the acetic acid, 140 from the hydrochloric acid, makes a new total volume of 515. So once I punch that in, moles, 0.350 moles of HCl, or so H plus from the HCl rather, 515 milliliters for the new solution volume, and that gives me a new concentration of 0.0680 moles per liter of H plus ions coming from the HCl, and I can punch this in here. The next step is to find out how much H plus is released by the CH3COH, the acetic acid. Unlike the hydrochloric acid, which is strong and 100% gives up all of its H plus ions, the acetic acid is weak. It is not on my list of 6 acids, so it's weak, and it does not release all of its H plus ions. So we need to calculate how much of the H plus ions are actually released. So we'll set up an ice chart to find out how much H plus is being released. But here's another common mistake that students will make. They'll punch in the 0.450 molar concentration directly into the acetic acid. But again, if you recall over here, the 0.450 molar acetic acid is no longer that concentration because you have a new volume. You've diluted it further. So we have to recalculate the concentration of acetic acid. Going back over here, mole is equal to concentration times volume. So the original concentration was 0.450 molar. Original volume was 0.375. So the original amount of CH3COH floating around solution was 0.169 moles. From there, divided by the new volume, which is 0.515 liters, and we get a value of 0.328 moles per liter as our new solution concentration. And so we can delete the old solution concentration and punch that one in over here, 0.328. Alright, so since the acetic acid hasn't had a chance to ionize yet, to break up into its ions, we're going to write down 0 and 0. Which means the reaction can't go in reverse because there's nothing here to react. So it must go forward, meaning this is going to be a minus x value. This will be a plus x, since it's a 1 to 1 to 1 ratio, so that's fine. And at the end, you'll have 0.328 minus x, x, and x. And this is where we'll encounter another common mistake that students make. You see, the H plus concentration initially isn't actually 0. There was some H plus floating around originally, and it all came from the hydrochloric acid. So because the hydrochloric acid gave up a lot of its H plus ions, 0.0680 moles per liter, it's not 0 over here. It is 0 from the H plus from the acetic acid, but it's 0.0680 from the hydrochloric acid, which means my final H plus concentration at equilibrium is X plus 0.0680. So please be very careful. This is a very, very common mistake for my students to make. All right, so zooming out, what we're going to do now is solve for Ka, or rather we can write out the Ka expression. So Ka is equal to the ionized component divided by the unionized component, products over reactants if you will. The Ka value for acetic acid can be found from our reference sheet, the blue reference sheet of 1.8 times 10 to the power negative 5. And then we can punch in all these X values into our expression here. To simplify this calculation, I'm going to use the assumption rule. As a reminder, we take the initial concentration divided by the Ka value. If that ends up being greater than or equal to 1,000, that means that your X value is negligible in comparison to the actual number you just tested against. So using the assumption rule, I tested against this one over here and this one over here, and I found the X values in both these cases are negligible. So X plus 0.0680 might as well be 0.0680. X, 0.328 minus X might as well be 0.328. Once I simplify this entire expression and solve, X is now equal to 8.68 times 10 to the power negative 5. Alright, so I'm going to take this X value and push it in here. Then adding up the concentrations of H plus from the HCl and H plus from the CH3COH gives me a 1.17 as my final pH value. Alright, so let's start our lesson on salt hydrolysis. If you recall, a salt is an ionic compound that results from an acid-base neutralization reaction. Alright, so during neutralization of an acid or base, you'll make salt and water. Now, salts are strong electrolytes. And if you recall, electrolytes are aqueous solutions that conduct electricity, so they have ions floating around. And that's what a salt does. When salt is placed in water, it completely ionizes. And in some instances, these ions can affect the pH of a solution. Now, if I were to ask a grade 10 or grade 11 student if NaCl, table salt, was acidic or basic, they would say neither, because it doesn't contain any H plus ions to make it acidic, doesn't contain any OH minus ions to make it basic, so the salt would not consider to be acidic or basic. So how is it possible for a salt to affect the pH of a solution? Now, I'm going to skip ahead a few slides. This is one of those situations where it won't make sense until we do a sample question. Let's take a look at ammonium chloride. If you look at our reference sheet, you'll find that under the chloride section, ammonium chloride is not present. So that means its KSP value is very large and ammonium chloride is very soluble. So that being the case, ammonium chloride solid will 100% dissolve in water, and when it dissolves in water, dissociate into its ions, ammonium ions and chlorine ions. Now, if you recall, the topic of this lesson is salt hydrolysis. Hydrolysis means to react with water. So the salt will react with the water. So what we're going to do is we're going to take the ammonium and react it with the water and see what will happen. Please make sure you write water as HOH, hydrogen hydroxide. It makes it a lot easier to visualize how the water will interact with the salts if you can separate them into hydrogen and hydroxide components. So here we have an example of a single displacement reaction. The positive charges will switch places, and you'll have a hydrogen ion being released and ammonium hydroxide being created as well. So as you can see, the ammonium chloride salt doesn't release the hydrogen ion to make it more acidic. It's how it interacts with the water molecule and forces the water molecule to release the H plus ion. Now, because there's H plus ions floating around, the solution is considered to be acidic. Now, some students ask, there's a hydroxide over here. Why doesn't that make it basic instead? Well, if you take a look at this, ammonium hydroxide, it's not a strong base. Only group 1 and group 2 hydroxides are considered to be strong. So this hydroxide is still stuck to the ammonium. It's not free floating. It doesn't affect the pH concentration in the solution. However, the H plus is free to move around, and that is what affects the pH and makes it acidic. But what about the chlorine? We also have to take this into consideration and see how will the chlorine ion react with water during salt hydrolysis. In this case, the anions will switch places, and you get a hydroxide being released as well as an HCl. However, what do we know about HCl? It is a strong acid, and strong acids 100% break up. So the moment you try to create this HCl, the reaction will go in the other direction over here and 100% break up, and so therefore there is no reaction in the end because you can't make HCl this way. The moment they try to come together, they will dissociate back into the original components. And thus Cl- has no effect on the overall pH of the solution. So we say the chlorine anion is a spectator ion. So spectators don't actually participate in the sport, they just watch. Well, same thing. The only one that actually participates in the salt hydrolysis is the ammonium component. The ammonium component will undergo salt hydrolysis, reacting with the water, to produce H+ ions and ammonium hydroxide. Ammonium hydroxide is a weak base, so it's allowed to stay stuck together, which means the H+ is allowed to float around, and that affects my acidic solution, or makes my solution acidic. Versus chlorine, when we try to react with water, it'll try to produce HCl, but that's not allowed. HCl will break up back into this, and so the Cl doesn't actually react with the water. The Cl doesn't actually do anything overall. It is a spectator ion. So that's why this component over here has no effect on the overall pH of my solution. Only the ammonium has an effect. So therefore this salt, ammonium chloride, will make my solution slightly acidic. It's not going to be very acidic, but it will make it slightly acidic due to the H+ ions that are floating around in my solution. Alright, so NH4Cl will make my solution acidic. So what I want you to do at this point is press pause and try out these 3 salts and tell me, will these 3 salts make my solution acidic, basic, or will have no effect and make my solution just neutral? Alright, so let's try the FeI3 and see how that will undergo salt hydrolysis. Again, looking at the blue reference sheet, we see that the FeI3 is not present under my KSB section, so we can assume that iron 3 iodide is completely soluble. So the solid iron 3 iodide will 100% break up in water, dissociating to the ions iron 3 plus and 3 iodine ions. Let's check and see how each of these ions will react with water through salt hydrolysis. So Fe3 plus aqueous plus water, hydrogen hydroxide. This again looks like a single displacement reaction. So the iron 3 and the hydrogen ions will switch places, resulting in an H+ ion being released and iron 3 hydroxide being created. Now if you recall, iron 3 hydroxide, not a strong base, not one of the group 1 or 2s, so therefore this is allowed to stay together and the hydroxide will stay stuck to the iron for the most part. Very little of it will break up, and so this hydroxide has very little to do with the overall pH of my solution. It doesn't really affect it too much. However, there is a lot of H+ floating around, so if there's a lot of H+ floating around, my solution is acidic. Now let's take a look at the iodine component and see how that will react with water. So we're going to have the iodine anion switch places with the hydroxide anion, forming a hydroxide ion and hydrogen iodide. Now hydrogen iodide is a strong acid, and what do we know about strong acids? They completely break up, so this reaction cannot occur. Therefore the iodine is a spectator and will have no effect on my solution pH. Thus only the iron 3 component will have an effect on my pH, making it acidic. So this too will also be an acidic solution. Let's take a look at potassium fluoride. Again, looking at the KSB chart, I don't see potassium fluoride on the list, therefore it's a soluble salt, 100% breaks up, releasing potassium ions and fluorine anions. Let's take a look at the potassium part and see what that will do when it reacts with water. The cations will displace each other, releasing H+ ions and potassium hydroxide. But with potassium hydroxide, that is a group 1 hydroxide. And we know that group 1 hydroxides are very strong. And if they're very strong, they'll 100% break up. So you can't have K and OH stuck together because the water will split them apart, dissociate them 100%. So therefore this situation results in no reaction. And potassium iodine is my spectator. Because it doesn't do anything, has no effect, it will not react through salt hydrolysis with the water. Let's now take a look at the fluorine and see how it will react with water. The anions will switch places, producing a hydroxide ion and hydrofluoric acid. Now HF is a weak acid. It's not on my list of strong acids. It's a weak acid. So if it's a weak acid, it won't break up. This fluorine, this hydrogen will be stuck together, so this hydrogen has no effect on pH, but there are hydroxides floating in solution. So if there's hydroxides floating in solution, that makes my solution basic instead. Alright, so the potassium fluoride salt will release potassium ions and fluorine anions. The potassium is a spectator because when you try to react with water, you would form a strong base. That's not allowed, and so that reaction won't occur, so it's spectator. But the fluorine can undergo salt hydrolysis, reacting with the water to produce hydrofluoric acid, which is allowed because it's a weak acid. It'll still stay stuck together, but there will be a hydroxide ions floating around solution, which makes my solution basic overall. So I'm going to write down basic. Let's take a look at KNO3. Nitrates are very soluble, so you won't even see a category for nitrates at all on my KSB chart. So you can assume that that is going to 100% dissolve and dissociate in water. So let's check each ion individually and see how they will react with water. As we saw before with the potassium, when it reacts with water, it produces a strong base. This is not allowed. The strong base will break up 100%, so therefore no reaction, and the potassium is a spectator at that point. With the nitrate, it will push out the hydroxide, and you'll get a hydroxide ion floating around, and HNO3, nitric acid. Again, nitric acid is a strong acid, so you can't have this form. All right, it will 100% break up. Therefore, this also results in no reaction. So neither of these two anions will result in salt hydrolysis, and so they're both spectator ions. So if neither of them allow you to form H plus or OH minus, my solution over here is neutral. So I'm going to write this down as a neutral solution. And there you have it, salt hydrolysis. So when you have salts, chemical compounds that will 100% break up in water, releasing their ions, there is a chance that their individual ions can react with the water to either release H plus or release OH minus from the water itself, or force the water to release the H plus and force the water to release the hydroxide. So depending on what's released, the hydronium or the hydroxide, that'll determine whether it's an acidic solution due to the salt or a basic solution due to the salt. And if neither the cation nor the anion will undergo salt hydrolysis, neither of them will force water to release H plus or OH minuses, then that salt is considered to be neutral. But what happens if you have a salt where both the cation and the anion can undergo salt hydrolysis? So they release both the H plus ions and they release hydroxide ions. This is where you'll have to compare the Ka and Kb values to see which one is stronger. All right. So if the Ka value for the cation is greater than the Kb value of the anion, then that means it's going to be more acidic because this guy can release more H's than this guy can release hydroxides. And vice versa. If more hydroxides are released than hydroniums, then it's basic. And if both of them are the same, then it's going to be neutral again. But for this course, we're not going to pay too much attention to this kind of situation. Primarily, we'll be looking at these scenarios over here where it's just definitively an acidic, basic, or neutral solution due to salt hydrolysis. All right, so this leads to our next topic, buffer solutions. Under most conditions, the addition of an acid or a base will result in a pH change for the solution. All right, if you add an acid to a solution, pH will decrease. Add a base to a solution, pH will increase. However, a buffer solution is one that minimizes or resists the change to the pH when small amounts of a strong acid or a strong base are added. Now, buffer solutions are very important to many biochemical processes, especially the ones in our bodies. For instance, our blood pH cannot shift more than 0.2 in either direction, otherwise you get extremely sick, if not fatal. So it's very important for us to know how it works. So, a buffer solution must have the following characteristics. It must contain enough acid to neutralize any base that you may add in. It must also contain enough base to neutralize any acid you have in there. And finally, the acid and the base that you have in the solution cannot neutralize each other. And that's where students usually get confused. How can you have an acid and a base in the same solution that won't neutralize each other? And that's where salt hydrolysis comes into the picture. We can create buffers by combining a weak acid and its conjugate base, or by taking a weak base and its conjugate acid. The key is to make sure that the buffer solution only contains weak acids and weak bases so we can have a dynamic equilibrium. You see, buffer solutions take advantage of the common ion effect, and this prevents the equilibrium from shifting too much in either direction, thereby minimizing any pH changes. Let's take a look at this example over here. If I put ammonia into a solution with ammonium chloride salts, I create a buffer solution. So let's take a look and see how ammonia reacts with water. I'm going to write water out as hydrogen hydroxide just to make it easier for us to visualize everything. So ammonia is going to grab the H plus ion towards itself to make ammonium. So if remember, base is gain, so this is my base, and now it's turned into a conjugate acid. And because the water lost the hydronium, it's considered to be an acid. Acid is loss, and therefore it turns into a conjugate base on this side. Now, if you recall, a buffer solution must contain enough acid to neutralize any base that you add in. So if I add a base, I increase the hydroxide concentration. Well, according to Le Chatelier's principle, if you increase the hydroxide concentration, equilibrium will shift in this direction and create more ammonia and water, thereby reducing the hydroxide concentration. So therefore, your pH has not changed as much as it could have, thereby buffering the solution. Now, as we saw with ammonium chloride, it is a salt, and so it 100% breaks up into ammonium ions and chlorine ions. We don't care about the chlorine ion. It's going to be a spectator, because if it tries to react with the water, you would make HCl. HCl is strong. We know that doesn't occur. It's going to 100% break back up, and so the chlorine acts as a spectator. So I'm not going to worry about the chlorine part, but I am going to worry about the ammonium part over here. As we had mentioned, a buffer solution must also contain enough base to neutralize any acid that may be added. So again, if I add acid to my solution, I increase the hydronium concentration floating around in my solution. And of course, according to Le Chatelier's principle, by shifting this equilibrium to the left, we can reduce the amount of acid that's in my solution. Because if you have too many of these hydroniums, they're more likely to collide with NH3 to produce this side of the reaction instead. And again, I have reduced the change in hydronium. It could have been as bad as this, really drastically changed my pH, but instead it only changed by this amount. So it minimized the solution, the pH change, thereby buffering it. Now here's the important part. In the buffer solution, we've seen how there's acid to neutralize any bases you add in. There's base to neutralize any acids you add in. But why and how can the acid and the base not neutralize each other? Notice how the ammonia and the ammonium are acting as conjugate acid-base partners. When the ammonia changes into the ammonium, it also has a chance to change back into this. So if we ever have a situation where, let's say, I increase the hydroxide concentration, well, now it's going to shift in reverse, bringing it back down, all right? But that means I got to consume the ammonium. The ammonium must reduce as well. Well, the ammonium will never get completely eliminated, because if this gets too low, the reaction will then shift in this direction, and the ammonia will replace and replenish the ammonium. So you'll notice that these conjugate acid-base pairs, these two over here, are backing each other up. They are there to prevent each other's levels from getting too high or too low. Same thing over here. If we add acid to the solution, this concentration will increase. The reaction will drive in reverse, going back down this way over here to minimize the change in pH. And that way this one will decrease and this one will increase. And of course, if this concentration ever got too low, then the reaction would go in the opposite direction and replenish this concentration. So once again, a buffer solution must contain enough acid to neutralize any bases you throw in there. It must contain enough base to neutralize any acids you throw in there. And finally, the acid and the base components of the buffer solution can't neutralize each other. And they can't neutralize each other. If this one gets too low, it will shift in this direction to bring it back up. And vice versa. If this one gets too low, it'll shift in this direction to bring it back up. So they're always there to ensure a balance, a dynamic equilibrium being established between the two. Now, some students ask, why do we include the chlorine if it's a spectator ion? All right, so if we're not going to use it, why bother with ammonium chloride? Why not just have ammonium by itself? The reason is because ammonium is a cation. It's never found in nature just by itself. It has to typically come in the format of a salt. So when we pick ammonium chloride, or rather some sort of a salt, we always want to make sure that this part, the one that we want in our buffer solution, is bonded to someone that will end up being a spectator, that won't affect the overall reaction. All right, so you can't pick a ammonium fluoride, for instance. That would be a bad example of a buffer solution, because the fluorine would make hydrofluoric acid, and the hydrofluoric acid is weak, and that would interfere with the buffer solution. We want to always have some sort of anion, in this case chlorine, that results in a strong acid being formed, which we know is not loud, and therefore will not have an overall effect upon the reaction. So it must remain a spectator. Alright, so one of the difficulties students have with buffer solutions is identifying if a buffer solution even exists, or how do I make a buffer solution itself. So what I want you to do is take a look at these guys over here, the weak acid, try and match up which weak acid is related to which conjugate base, because those two pairs will make a buffer solution. So I'm going to let you press pause. When you're ready, press play and we'll go through the solution together. Alright, so if you recall, base is gain acid is loss. So if we're dealing with weak acids, they have to be the ones that lose protons. So the only difference between a base and its conjugate acid, or an acid and its conjugate base, is they must differ by just one H plus ion. That's all they can differ by, all right? So looking at HCOH over here, if we got rid of one H, because it's losing an H plus, then it looks like this one. Therefore, this must be its conjugate base. Similarly, HC2O4, when we lose this H over here, it will look like this one, C2O4. And then, of course, when this one loses an H, it'll look like that. And when this one loses its H, it'll look like this. And again, base is gain. So whoever gains an H should be its conjugate acid at that point. So NH3, if you give it an H, should look like this, NH4+. HC2O4, give it an H, and it'll look like that. C2H5NH2, gain an H, it'll look like this. And by default, you've got that one. So make sure you can recognize conjugate acid-base pairs because they are used to back each other up in buffer solutions. Alright, so in this last activity, what I want you to do is identify which of these pairs will form a buffer solution and which ones will not form a buffer solution. Alright, so press pause, and then when you're ready, press play, and we'll identify which one of these is a buffer solution. Alright, so the first example, let's see if there is a conjugate acid-base pair, because if you don't have conjugate acid-base pairs, you don't have a buffer solution. So NH3 versus NH4, do they differ by just one H? They do, so they have the capability of making a buffer solution. And then, of course, NO3 is a spectator ion. How do I know it's a spectator ion? NO3 plus water would result in you producing HNO3 and hydroxide. And of course, we know HNO3 is strong, so there's no way this could form, so it's just a spectator ion. I don't have to worry about this one. I just have to worry about these two. The last thing we need to check is to make sure that neither of these are strong. They're both weak, because you can only have an equilibrium if they're both weak. If you have a strong acid or base, there is no equilibrium. They 100% break up. Well, these two are definitely both weak. They're not on my list of strong acids, strong bases. So yes, this is definitely a buffer solution, or could be a buffer solution anyway. In our next example, we can't have a buffer solution here because HNO3 is a strong acid. Remember, buffer solutions only exist when you have a weak acid or a weak base to form an equilibrium. This strong acid would not allow you to form an equilibrium, so therefore, no strong acid, so it's not a buffer solution. Looking over here, I recognize everyone is weak. None of these are strong acids or bases. The sodium over here is going to be a spectator ion, so I don't have to worry about that one. So take a look at this. Na would make NaOH and an H plus ion being released. Sodium hydroxide is a strong base. That can't form, so no reaction. So I can recognize here that the sodium is a spectator ion. Don't have to worry about this one. Just worry about these two over here. Now, do they differ by just one H? Absolutely. So we can consider it to be a buffer solution. On to the next example. Again, we have the sodium over here, and I could ignore sodium. Again, another spectator. Don't have to worry about that. But the HC2O4 versus H2C2O4, these are both weak. They're not on my lists, so I can consider them to be weak, so that passes one of the tests. Do they differ by just one H? Absolutely, they're differing by just one H. So yes, we can consider that to be a buffer solution as well. Now, right off the bat, I know that this can't be a buffer solution because the sodium hydroxide is strong. Again, you can't have any strong acids or strong bases in your buffer solution. There is no equilibrium there, at least none that you can use anyway. Over here, again, I don't need the sodium part or the sodium part. That is just spectator ions. But HC2O4 versus C2O4, they are both weak because I don't recognize them. And do they differ by just one H? Yes, they do differ by just one proton. So yes, we can consider it to be a buffer solution. Once again, I can ignore the sodium over here. And the C2O4 and the H2C2O4, I don't recognize these as part of my list of strong acids, strong bases, so they're definitely weak. But do they differ by one H? No, they differ by two hydrogens. So conjugate acid-base pairs can only differ by a single proton. If you have too many protons difference between them, they are not considered to be conjugate acid-base pairs, so the salts must be conjugates of each other. Finally, the last one over here, again, I don't have to care about the sodium, but HC2O4 versus HCOH, I mean, these guys don't even look the same. 2 oxygens versus 4 oxygens, so they can't be conjugate acid-base pairs because they can only differ by 1 H plus ion, so therefore no buffer solution there either. Alright, so let's watch a quick video on how buffer solutions maintain our blood pH and keep it constant, preventing major swings in either direction.
The blood system of an adult person contains about 5 litres of blood, a liquid that carries nutrients and oxygen to all living cells in the organism and removes waste products. One of the most important functions of blood is to provide oxygen for cell metabolism and remove the waste product, carbon dioxide. This process is quite complex, and its effectiveness is strongly affected by the pH of the reaction medium. Therefore, the pH of blood plasma is carefully controlled by the organism and maintained at a constant level of 7.4. The pH inside the erythrocytes is a little lower, about 7.25. Effective control of the pH is possible because blood contains a certain amount of carbonic acid, which is a weak diprotic acid, and also a certain amount of its conjugate base, the bicarbonate ion. The delicate balance between the concentrations of these two species.
So as you can see, the carbonic acid and its bicarbonate ion, they're acting as conjugate acid-base pairs, whereas this is the acid because it loses the H+. This was the base because it gains the H+. They act as a partnership. So neither of them can eliminate each other. If this one gets too low, you'll shift in this direction to replenish it. If this one gets too low, you'll shift in the reverse direction to replenish it. But also, they are able to neutralize any acids or bases that are added to the blood. If too much acid is added to the blood, the H+ concentration will rise, again shifting the equilibrium back in this direction, reducing the H+. And vice versa, if the hydroxide concentration gets too high, it'll shift in the left, reducing the hydroxide concentration back down. So once again, buffer solutions can neutralize acids, can neutralize bases, but they won't neutralize each other. And this is what keeps the H+ ion and the hydroxide ion concentrations fairly consistent, thereby keeping the pH of the blood fairly constant as well.
Allows the pH of blood plasma and erythrocytes to be maintained at a constant level. Solutions containing weak acids and their conjugate bases are capable of maintaining their pH at a certain stable value. Such solutions are called buffer solutions.
Okay, so what I would like you to do now is work on this handout. This handout has answers at the back for numerical answers only, doesn't have any full solutions. Just be aware this is not my worksheet. This belongs to someone else. I found it online. I don't remember where I found it from. The reason why I say that is because I have no clue what these things are. I think they're supposed to be inspirational quotes, but they don't make sense to me. Anyway, so give it a try. If you have any questions, please let me know.